So if I give you 2 points, x naught, y naught, and x1, y1, you can always create a vector between them. And it's just like when you were in algebra, in a sense, you're looking at the delta y and the delta x. You see, that's kind of glary. Let me try it without the light. You guys have a preference? It's a little dark there, but with the light, it's pretty glary. Does that look okay? Okay. So you're just doing subtraction. The distance from the first x naught to x1 right here would be the subtraction of the two. So it'd be x1 minus x naught. And then the same for the y's, y1 minus y naught. We tend to call these, so if I call the first one A and the second one B, then we call the resulting vector AB. Does that make sense?
Yeah, yeah. I just wanted to like I guess the visual helps because I was like, what's the direction? What's the yeah, so that totally helps.
You will find that most of the time it doesn't matter. However, it's best to just go with what you're given. If you're given A, B, just go with that, and but be consistent. That's important. So if you're gonna, go x1 minus x naught, but then don't do y naught minus y1. Don't switch that. You need to be consistent. All right. So in general, how do you guys do with the vectors?
I lose a negative a lot.
So what?
I lose a negative a lot. Sometimes I
Okay.
try to do too much in my head.
Okay. Yeah. Ironically enough, the most challenging thing of these vectors is the arithmetic. It's the little stuff. It's adding and subtracting. So and messing around with minus signs. So as you work these, just be careful. I tell my students, whether online or in person, just go slow, be methodical. It's the little things that are going to surprise you.
Yeah, I have a lot of notes in my homeworks that are just simple arithmetic and you're tired.
Yeah.
So
There's a question from, will the matrix calculator? Yes, I make the matrix calculator available on the tests. This is the Desmos matrix calculator.
And
I
so
give
I,
you,
I have a question.
yeah,
Yeah, so on the homeworks, so for the most part, I think I'm pretty solid on the vectors. The questions that trip me up are the real life ones. So like the one that was in what topic? I think it was 10.4, where it was like the ladies pushing a box
okay.
diagonally at a 30-degree angle, blah 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 blah. Those questions trip me up
Let's
almost
take a
every
look.
single time. Yeah, and I can
Uh,
find what number it is here.
10-4 would be the cross product. I think you're thinking of
Yep.
the dot product because if like you're talking about work.
Oh, yeah, yeah, yeah. Yeah, that one would be the work question.
Give
But
me a
there was
second.
one kind of similar in the
Okay, I think I found one.
dot product as well,
is
or
it
cross
is
product.
it 10.311, Sandra?
Yeah, give me a second. I'm
Yeah.
going to share it.
I had that one too.
This one right here. A woman exerts a horizontal force of 10 pounds on a box as
Yeah.
she pushes it up a ramp that is 1 foot long and inclined at an angle of 30 degrees above the horizontal. Find the work. Let me copy that down. Um, so the ramp itself is a foot long, 30 degrees, and she's putting a horizontal force. That's important.
Is it possible to stop sharing your screen so we can see what you're writing on the other?
Yeah. I'm gonna make it bigger. I'm copying the information down from my own. Uh, so I have to copy it. All right. So now I'm gonna share my screen or stop the share. There's a couple ways to do this particular one. You can just do old-fashioned physics, and we just need to figure out. Well, she's again. I'm going to refer to the problem here because um, in this particular case, let me in general, if you have two vectors u dot v, their formula. This is one of the formulas. Okay. And so, in a sense, you can get away with doing this problem right here. You're doing 10 pounds, so 10 times 1 times cos 30, which should be rad 2 over 2. No, I'm sorry, rad 3 over 2. There should be 5 rad 3. Get my calculator here. And I get 8.66 pounds. Now that's just using physics. So she's pushing horizontally, and so some of that effort is being put. I guess she's pushing it into the uh, platform, if you will. And so, could we do this using? Let's try to do this using vectors. So the force vector would be 10 and 0. Okay. And then what I would do on this problem is I would take this ramp here and I would just break it up into its two vector components. We'll call it R for ramp, I guess. And it's 1 cos 30, 1 sine 30. Now, normally I wouldn't write the 1, but I'm doing so to illustrate um, how you decompose a well, essentially a right triangle. So if you're given information about the hypotenuse and the angle, here's how you decompose basically the adjacent and the opposite parts. And notice that, well, okay, I'm using UV here, but F and R, if I dot them, well, I get 10 dot that, so 10 cos 30, and then plus 0 dot that is nothing, so 10 cos 30. And I get the same thing I had up here, which is going to be rad 3 over 2. I have to kind of memorize that one. Yes, rad 3 over 2, so the 5, you get 5 rad 3. But remember also that by definition, the dot product is mag F times mag R cos of the angle. So that's why this formula here from physics can easily be adapted. I noticed that, obviously you guys get separate problems. It's the same problem, but you might get like, 5 pounds and a ramp that's 3 feet long, for example, at a different angle. So it's the same type of problem. The numbers are randomly chosen. In my problem, I had a 1, which I kind of don't like because you lose some stuff there when you do that. But anyway, it worked out just fine. It works the same way. So one of the immediate applications of the dot product is work. And later on,
Oh,
go ahead.
sorry. I was gonna say, is this essentially the same thing as doing work equals force times distance?
That's exactly what it is.
Okay.
Because you're applying a force of 10 pounds, and now she's pushing it up a ramp that's a foot long but elevated at 30. We want to look at the part that's going in the direction. We want to look at the part of the triangle that corresponds to this 1 foot at an elevation of 30 degrees. Does that make sense?
Yeah.
So I guess you could say she's actually pushing it this distance horizontally, even though the object will eventually go up the whole ramp. This is the horizontal distance that it'll travel.
And so it's just gonna be a thing of the more you do, the more you kind of understand what to apply where type of situation for these then.
Well, yes. Yes, in a very real sense, the more you practice this, the more it becomes, well, hopefully mechanically it becomes just easier, but also hopefully you start seeing how these can be applied.
Hmm.
It doesn't all happen at once. You're not going to open up a homework set and just know everything. And that's part of the challenge of learning any subject is it comes in bits and pieces. And then at some point it starts to take shape. And so what you guys are experiencing right now is that you're basically just jumping in, doing problems. You may be doing them blindly. You might just be copying a formula and plugging the numbers in, but that's okay because every little bit helps. What I usually ask is just don't get discouraged. Get frustrated, that's okay. Don't get discouraged. If you hit a problem that just absolutely stumps you and it's the middle of the week or whatever, put it on ed discussions because I'm always checking that.
Do you recommend that we make use of the 3D Desmos thing? I don't probably won't be
Yeah,
available on the test, but just for like getting an
yeah.
understanding of the
Actually,
way.
yes. When you get to that section where we start doing a lot more graphing, yeah, absolutely. Um,
I
Go
I have a
ahead.
question for in 10.3, number 9.
10.3, number 9. All right. Since I already got it up, I'll bring it up here.
Perfect.
So I'm going to share it real quick. 10.3, number 9. Oops. Well, I went too far back. This one. The famous Gandalf the Grey.
Yeah, there's a couple of those, but so I guess to start off with, it's not I guess it might be apparent that you're using a projection vector since it is
Uh-huh.
that section, but just reading it, if the help button wasn't there, I wouldn't know that we're first using projection. And then also I wouldn't know that you're subtracting v minus the vector that we create from the 2 points. So I guess I kind of what makes it apparent that we're using projection vector here first?
Well, I'll draw you a picture. And so right now I'm copying the information onto my thing, and then I'll share my overhead. 3, 1 plus 2j, 3i plus 2j. All right. So Gandalf the Grey starts in the forest of Mirkwood at a point P, coordinates 3, -3, and arrives at the Iron Hills at point Q with coordinates 4, 1. But unfortunately, he starts walking in the direction of 3i plus 2j, and he's allowed one right angle turn. All right. So I've got the picture drawn. All right. So he's here. He wants to end here, but for some reason he starts walking this way. And he's allowed one right angle turn. If I eyeball it, it'd probably be right about there somewhere. Okay. And so what we want to figure out is what's the coordinate of that turn. And as I draw the picture, I'm going to draw a vector from P to Q. I'll call that vector, since everybody's using V, I'll call this one U. And I'm doing the subtraction trick. 4 minus 1, 3 is 1. 1 minus -3 is 4. Okay. So a shape takes a, a very well-known shape starts to form here. It's a right triangle. Okay. And here's a big hint. projections are pretty much hand in hand with right triangles. So if the problem starts to, if you sense when you're sketching the picture out that it's involving a right triangle, you're going to be using projections. So essentially what we're doing is we're decomposing this vector u, which is the hypotenuse, into two smaller vectors, one that's parallel to 3, 2, it's going to be this guy right here. Now, and then this one right here. Now, we don't necessarily need to know this vector. We just need to know what this point is. But for future reference, once you get two vectors, you can always just subtract to get the third. Now, the question then becomes what projects onto what? And another big hint, always project the hypotenuse. I've spelled that wrong. Hypotenuse onto the adjacent leg. Always, 100% of the time, you're projecting a hypotenuse onto the adjacent leg. So by drawing a picture here, you hopefully you see that this is the hypotenuse and this is the adjacent. Now, let's say you're still kind of stumped about that. Well, the hypotenuse is always opposite the right angle. So if you determine where the right angle takes place, then that establishes where the hypotenuse has to be. So I'll pause here for a moment. Does that make sense? Got the hypotenuse, I've got adjacent.
With how it's laid out like this, it makes a lot more sense than how I read it and interpreted it. So just getting to this point from here, I understand how to do the projection portion of it. And then the
Okay.
last portion of it where in the help it says subtract v minus the whatever vector that we created. I don't fully understand that
Okay.
part either.
Well, let's go ahead and do it. I mean, I might as well. I've got all the stuff here. So it's a projection of, we're projecting u onto v. So it's u dot v in the numerator, v dot v in the denominator, and all that times v. So what's happening is v is going to be lengthened or shortened. All the action's happening on v. And so now u dot v is going to be 1 times 3 plus 4 times 2. It's going to be 3 plus 8 is 11 in the numerator. V dot v is, well, that's going to be 3 squared and 2 squared, so it's going to be 13. So 9 and 4 is 13. And then v is being altered. I'll go ahead and distribute that. I get 33 thirteenths, 22 thirteenths. Okay. Now, that doesn't quite yet answer the question. Everything's been offset from the origin. If Gandalf had started at the origin, if we just simply rigidly move this whole thing so that the starting point was at the origin, then we would have our point, because this vector would actually correspond to the point of where you make the right angle turn. And so generally you just subtract. So let me write this out. So to account for the original location, the original. I'm going to subtract it off from what you see here. Actually, I want to take that 3 minus. Give me a second here. I'm having my own. If I do 3 minus 33 thirteenths, I don't think that's right. I'm going to try it.
I thought we added point P to the projection that we just did.
Yeah,
I was gonna
yeah,
say
that
the
makes
same
sense.
thing.
That makes a lot more sense. Because I was having a little doubt. I was saying subtraction, and I was thinking that doesn't seem right. Yeah, so we're adding. Yeah, we'll call it add the start point. So that becomes a plus. And then -3 plus 22 thirteenths. Now I'm gonna go ahead and just work it out. 3 plus 33 thirteenths. So it's about 5.538 Then I have -3 plus 22/13. That's about -1.308. Now here's the thing. Way back before I even started the question, working out the math, I figured out that the right angle turn has to occur right about where the dot is, where my pen is. Now, if I draw my graph carefully, I tried to draw it accurately. I was trying to be consistent with the scales. So just kind of like that. Does the answer I get here seem to agree with the basically the eyeballing answer I got here? Do the numbers seem to match?
Yes, sir.
Yeah, so that means that's a good indication you did it right. So I'll just, whoops, come on you. I'll just mention that it seems to match well with the drawing. So when you're doing these kinds of questions, do a really detailed sketch. Try to draw the sketch as carefully as possible. So sketch the scenario accurately. So try to be consistent with your scale, and that way you have something to build off of, and then your answer should agree with the picture you drew. One other thing about infinity is it can be a little picky. It should accept this. If you just typed it in as 3 plus 33/13, comma, -3 plus 22/13, it should be just fine. Because 13 is kind of an oddball denominator, you're going to get this long decimal uh, part. I only took it out 3 places. I would actually probably, for infinity, I'd probably take it out 4 or 5. You might
The
have,
the home the
what's that?
homework is actually pretty lenient on not reducing and having improper fractions, stuff like that. The only time it's ever really precise is when you're dealing with radians. It's usually to 3 decimals, but typically it's pretty lenient.
It is lenient. Yeah, I agree with you. It'll accept what would be these kind of unsimplified forms or this form is accurate. What I've noticed is some people will take this form and they'll type it like I did on my calculator, and they'll just chop it down. They'll let's say, okay, 5.5, 1.3. They're rounding too early. And it may not accept an answer like that. So be on the safe side. If you're going to enter decimal values, give it at least 4 or 5 places. Then you should be fine. And on a test, I look for that sort of thing. If you get the answer wrong, but you had the right number, you just didn't take it out far enough, I usually give you the points back.
On the test, do you want us to rationalize when we have a?
No,
Okay.
no, just get it right. Tim, did you have a question? Tim, I saw
Oh,
your hand.
yeah, sorry. That was the question on the test. So like if we have a radical on the bottom, do we want to
No,
rationalize that?
I don't care. You can leave your answers in unsimplified fraction. You can leave your answer with radicals that haven't been reduced. Um, what I would ask generally, if it's an obvious reduction, let's say you get 2/8, then go ahead and write it as 1/4. But even then, you'll get it correct, so it doesn't matter. If you get a radical like radical 64, that's going to be 8. But if you get some weird radical like 13,426, don't waste your time trying to reduce it. I don't care. The olden days when you were in grade school and middle school and they say, oh, you have to reduce your radicals. You don't have to reduce them. I don't care.
I'm old enough to remember having to do that. So
Yeah, same. And they always talked about, taking the radicals out of the denominator. But
yeah,
again, I don't care. It's as long as it's correct,
if it works, it
that's
works.
all I'm asking. So I'm going to share it 10 to number 11. Where are we going here? Oh, yeah, yeah. Let me get this drawing. So we got a horizontal clothesline. It's tied between two poles 10 meters apart. Mass of 3 kilograms is tied to the middle. It's going to cause it to sag. And it sags a distance of 5 meters. That's quite a bit. All right. So it's originally 10 meters apart. Half of that will be 5 and 5. And then there's this 5 here. We have a little angle kind of shoved in there on both of them. It's the same theta. Now, the downward force, we're going to have to multiply 3 times 9.8 for the gravitational constant. And so we have a situation here where so 3 times 9.8, I'll figure that out later. That's going to be counteracted by 2 upward forces, which are so we have tension. Let me put a little T here. Mag T for what's the actual tension. There's 2 of them. There's this tension times the sine theta. And there's 2 of them, one for each side. Okay. Now, before I jump into the solution, does that make sense why it's sine theta, for example?
Yeah, I
Okay.
think that's where my question was a lot like because I know from the lecture and the sample problem, it was like one was negative cosine theta, sine theta, and then the other one was cosine theta, sine theta, which then gives you the two at the tension sine theta.
Yes.
Sine theta is, opposite over hypotenuse, but I was just curious, like, why are you selecting sine versus, what what's the real reason why?
Well, there's actually there's the horizontal forces are actually canceling each other out. Okay. This is T cos theta, and this is also T cos theta, but they point in opposite directions. So the horizontal forces cancel. All right. And because this is symmetric, you can assume that these are the same tensions, just pointing the other way. Another way to argue that would be if I use the normal XY axis system, I put a little negative sign in front of this guy right here to indicate that it's going left, and this one will say a plus sign going right. And when I add them, I get 0 as expected. Okay. Meanwhile, you've got 2 upward forces. You got one here, and I'll put it right next to each other, one there from here. So you have both of these mag T's, which is the tension on the clothesline. We need to figure out the part that's horizontal, and that's where you get the 2 of these guys. So this is mag T sine theta, and this is also mag T sine theta. But because they're pointing in the same direction, they don't cancel. In fact, what they do is they combine and give you the 2 mag T sine theta, and that cancels out the downward force, whatever that number is. Okay. Um, Now, let me go ahead and figure this out. So we want to know the tension. So we're just going to divide 9.8 divided by 2 sine theta. Now, here's the question. We don't know what theta is, but we know what the sine of theta is.
Yeah.
You're just looking at your picture here. Well, let me just draw another triangle because it's getting cluttered. I apologize. We've got 5 and 5. And so the hypotenuse, so the angle's tucked in there. The hypotenuse will be 2, well, let's see, it's 5 squared plus 5 squared, so I'll just write it out. That's going to be rad 50 or 5 rad 2. Okay. And so here's the cool thing about this problem. You don't actually need to calculate theta, but you can calculate the sine of theta just by looking at the picture here. It's the opposite, which is 5, over the hypotenuse, which is 5 rad 2. Now, that gets a little ugly. Let me clean that up. 3, 9.8 on the top. 5's cancel, so I have 2 over rad 2 on the bottom. Go ahead and punch that out on a calculator. Just be careful with your parentheses. So 3 times 9.8, then, oops, come on, surgeon. And then divided by 2 over rad 2. So parentheses 2 divided by rad 2, close parentheses. And I get 20.789. That'll be newtons. Okay. So just for the heck of it, I'm going to figure it out. 3 times 9.8 is 29.4. Okay, that makes sense. Does that help whoever asked this one?
Yeah, I think the visuals of showing the tension of cosine, negative cosine, and that visual really helped me. So I appreciate that.
Okay.
So
Don't
Um,
put
I
the
mean, in this case, it's like you've got two equal length
Yes.
magnitudes, so it's kind of easier. But um,
If they're not, if let's say it's asymmetric, then you're going to have to work out a system. And I have a problem like that in my notes. It's kind of lengthy, but it shows you how to do an asymmetric case. I don't think you had any, I don't think you had any of those in your homework. Let me check.
Yeah, but it's in the typed examples for vectors. It's example 6.13.
Yeah. Yeah, that one takes that's going to take some work, no pun intended. But that's how you would handle it if it was non-symmetric.
Yeah, I think for most of these questions, the way I was going about it wrong is I wasn't doing a diagram first. I was trying to read the question and just put notes to it. But seeing how you work it out, you draw up your diagram first and then work it out. It kind of makes it a lot more easy to understand.
Yeah, I
Yeah,
agree.
and I can't do it any other way. I got to see it. I'm a visual person, and otherwise it is kind of tricky of like what numbers are getting plugged in where, and it just feels like I'm just randomly plugging stuff in and hoping I get lucky. So, like in that problem with the Gandalf the Gray, whatever you got to do, just draw a diagram. If it helps, just hopefully that helps you start to see it. Hopefully, you start to see the really important parts, which in a lot of these problems, we're basically dealing with right triangles.
I know there's no homework associated with this section, but do you have any suggestions for understanding 10.6, like the
Yes. Okay.
surface equations?
Um, that's the one that's just like, if I recall, isn't that the one that's just like a lot of common surfaces to look at?
Yeah, like the traces and
I would,
the rulings.
yeah, that might be where maybe looking at a 3D graph or online would be helpful. We used to do that. I think the problem is that it's something you really just have, it's almost like an art class. You have to just sit down and start drawing. The idea is to, it's almost like looking at a lot of functions and start to get a sense of what kind of shapes they make. We'll be doing a lot of stuff with paraboloids, spheres, ellipsoids, cones. where what the saddle-shaped objects. And then there's just a lot of things that just don't fit into any category. They're just crazy looking. And I would never expect you to hand draw such a graph, but definitely with an online grapher, you can do that. And now Desmos and also GeoGebra are pretty good at doing this. But I also find that when I just Google, let's say 3D grapher, sometimes I'll see one that I hadn't seen before. And some of them have pretty nifty little uh, features, like maybe doing a cross section. So to just experiment and see what's out there.
Okay, thank you.
Yeah, that's one of those ones where you're just looking at a lot of graphs and starting to get a sense of what equation corresponds to what graph. It's not so much you're doing math, you're just kind of getting a feel for what to expect.
Right. So in this section, when they talk about the traces, is this just like looking at this graph in 2D from different planes and then just like connecting it all in the end?
Yeah, pretty much. So if a paraboloid, for example, is a bowl-shaped object, okay? If I were to chop it with let's say the XZ plane, so this is X and this is Z. If I were to do a cross section, I would actually get something that looks like this. It would be a parabola on the XZ plane. So now, of course, my drawing is not very good, but you would get a kind of like a wireframe figure. You get a parabola going this way, and you get another one coming this way. Now, that looks terrible. You don't have any sense of depth perception. But the idea is to somehow infer that you get a three-dimensional object out of that. And that's not something I can so much as teach you as just to show you how the drawings look and hope that it connects when you're looking at it.
I
Okay.
guess something that I got out of the examples for point six, and I guess the lecture is to just really try to understand which direction it opens. So if X is constant, then it opens in the X direction or something like that, if it's a cylinder. Um,
Right.
that's kind of what I got out of it.
Um, and every chance you get, especially if you're doing your homework, graph it. See what the object looks like. So if the problem says a cylinder is intersecting a cone, well, try to graph them and see if you can see if that helps. The more you see of these things, the more they become familiar to you.
Will we have access to 3D Desmos for any, like during any of the tests?
Yeah, usually I make all of Desmos open. So I give you the main
Oh,
calculator
okay.
one, the matrix one, and then the 3D one. I forget what else there is. There's a scientific one. The main one will do what the scientific one does.
Right.
So I usually don't make that one available, but it doesn't make a difference.
Kind of on a similar note with interpreting graphs, kind of in the reverse pane, this is 10.7, but there was one question where it gave you formulas for curves and then asked you to interpret the graph and pick one. And
Right.
in Desmos, some of those graphs are like, it just looks like two lines. And
Yes.
I'm like, I didn't know there was any tricks, or I guess using the 3D thing would help. I wasn't sure if we would have access to that, so I didn't want to count on it.
Yeah.
But yeah, for some of
I'm
those, I
actually
didn't know.
looking at it. So 10.7 you said?
Yeah, it was number 5, I
All
think.
right. Yeah. All right, I'll click on that.
And
So
there
I'm
were
gonna
like two of
share it.
them that looked so similar, and they didn't even label the axes either, which was bizarre. But
Well, let me verbalize how I might approach this. Some of them just, first of all, for example, number four, I'll highlight number four. The X and the Y together, X is cosine, Y is sine, that's going to create a circle. Meanwhile, Z is sine of 5t, that's going to create a sine wave that's compacted. The period is very small. So it's going to be like a slinky in the XY plane, but in the Z direction, it opens up, but with very tight um, swirls. And now, if I click on these guys, you're not going to be able to see them. But I wonder if it's F. I'm going to click on F. Only because it seems like it's got the long axis. Yeah.
If you scroll down in the solution, it'll tell you which one it thinks it is.
Yeah, I was just trying to do this with the just kind of reasoning it out. With number three, for example, X and Y are making circles. Z is LNT. As T increases, LNT increases, but it starts, but not so fast. It's got to have to be C because it's going to start kind of, the little circles are going to start kind of piling on each other. For number six, X and Z together make circles. I'll bet you six is F. Yeah. Um, yeah, I mean, there's really no formulaic way to do these. You just kind of play with them. If you can, you know what you can do is in Desmos, you can take two of these at a time and graph them parametrically, and you can get a sense of what they look like. Let's say, for example, number one, you could take the X and the Y. What you do is you just simply type in parentheses, three sine 3t cos t, comma, sine 3t sine t, and then you play around with the t value and it gives you a picture, and that gives you what it would look like in the xy plane. Now z is t is just simply going to increase uh, in that in the direction of z. It's just simply going to be basically be, well, I don't know how to put it. It's increasing linearly. I bet you it's d. And as far as the other ones, gosh, I frankly, I would just start trying to do like two at a time and just see if I can't infer the picture that way. These are
Yeah,
not the
the
easiest
A and
looking.
B were the two that, like, those two graphs that caught me up a little bit because I was having a hard time identifying where it was intersecting with axes or even, you know, what exactly was going on there.
Right. I agree with you. Well, let's say, for example, Y, let's look at number five here. As these are all, well, then none of these are trig. So let's see, as T increases, X is going to increase, Z is going to increase, but Y is not. As T is increasing, Y is actually going to start to shrink towards zero. And so you should get a situation where on the y-axis the graph is kind of, well, it's not going to get very far from y equals zero. I'm wondering if that's, I see, ugh. Is it B? Yeah, it's hard to tell. I even have trouble with these. Um, you know what? Rather than worrying about whether these are formulaic or anything like that, just have fun with them. Play part. Once you get three or four done, obviously that's those are eliminated. Then on the other two, just maybe try to literally just plug in some t values and see what you can generate and see if you can't pin the graph down that way. These kinds of questions are usually not asked on exams. When I teach this class in person, I never ask these kind of questions because I don't want people to draw. I don't want to look at terrible drawings all night.
Would
I'm
you
going to
be
try
okay?
something.
Oh,
Give me a second here. I'm going to stop the share. I'm going to go to I'm going to try Desmos. Let's see. How do I do this? Let's see. All right, so I'm going to try something here. I'm going to go to, I'm actually, oops, one second. I'm going to go to Desmos. And I don't guarantee this is going to work, so bear with me. For For 2 dimensions, it's easy. You just type in the functions this way, and then you play with, let's say here it's going to be 6.28. There you go, a circle. Now for 3 dimensions, I don't know. Let's see what happens. Didn't like that. So I'm going to go back out. I'm going to try the 3D grapher. Let's see if I can do it in the 3D grapher. So I'm going to try, let's see, cosine t, oops, sine t, then 1. And I'm going to go from 0, how about to 13? No, that should be a t. Oh, okay. Now we're starting to get something here. Can you guys see that?
Yes.
All right. Well, try that. So on that problem, go to the Desmos 3D and then type in the problem in this manner and then play around with the bounds and see if you can't generate the graphs. So if I do ln(t), for example, yeah, you can kind of see that it starts to crunch up there. Let's go to 30. Yeah, there you go. It's pretty nifty. All right. Okay, it worked. Cool. So that's Desmos 3D, and then you just type in the X, Y, and Z in this fashion, and then play around with the T values, and then just have fun with it. All right, guys, it's 6:55 in Arizona. I'm gonna go ahead and kind of shut this down. I'll have the recording up in about an hour. And so again, I'll do this every Sunday, and then on tests, I'll just have to figure something out. So thank you all for joining up. And you just, in the meantime, just put your questions on Ed Discussions, and I'll make sure I take a look. I'm really pleased to see how much activity has been going on there. So I like the fact that a lot of other people are jumping in and helping each other out. That's cool too. So, well, y'all have a good evening and stay safe. Cheers.